Welcome to a quick lesson, some tips and tricks on how to deal with force problems and a basic overview of really what we need to be able to do for this unit. If we have an object that is experiencing some forces, we have to be able to do some basic analysis. That analysis includes coming up with all of the forces on an object, and the best way to do that is to draw a free body diagram in which we determine everything that is pushing or pulling and what direction those pushes or pulls are in. So we need to make sure that we come up with all our outside forces. Remember that an object cannot apply a force to itself, so all of these outside forces are going to have to be some other object, something from outside pushing or pulling on it. After we do that, we are going to need to write our sum of force equations, which I often just abbreviate like this. We'll need to do that for x and for y. And as we said in the notes, when you see this sum of forces, you should be thinking all the forces in one direction minus all the forces in the other. We want to do that for all the x forces. We want to do that for all the y forces. In the last unit, we talked in vectors and said often all you'll have to do is x and y, and you can stop right there. You don't need to combine them. And for most of our force problems here, that will also be the case. We can write a separate x equation, we can write a separate y equation, and often you won't have to do anything beyond that. You will not actually have to combine these forces. You'll get everything you need out of them. So let's look at one of the sample problems that we have on our force diagram and equations problem set. The little assignment where you had to go through and come up with free body diagrams and equations, because people tend to skip past these, but this is the biggest thing. So one of the situations that we had was a sled with a package on it is being pulled across the ground and speeding up. And we'll do just a little bit of quick explanation of where we got all of these, because we need to be able to come up with all of these forces. So a sled, and our question is, okay, what are the forces on this sled? Well, we can start with gravity, and that is the earth pulling down on the sled. There's a package on top of the sled. What direction does the package push? Well, if I've got my sled, and the package is sitting on top of it, it's pushing down on the sled. So that's why when I did my free body diagram, from the perspective of the sled, this is my sled right here, the package pushes down. Are there forces on the package, and are there forces upward on the package? Yeah, there's other stuff going on, but we're only worried about the sled right now, and one of the beautiful things is we can worry just about one thing at a time. We can just focus on the sled and not worry about everything else. So earth pulls down, the package is pushing down. Then we have this thing that we often get confused about here. It's called the normal force, and people, assume that it's something special. But when the most confusing question is, well, what is pushing up? And we need to be able to answer that. We need to be able to say that this sled is not falling downward, even though gravity pulls down, even though the package pulls down. The sled is not accelerating downward. Why not? Because the ground immediately underneath it is pushing up, and that's what this normal force is. So earth pulls down, the package pushes down, the ground immediately under the sled pushes up. Now it said those are all our up and down forces. What about our side to side? It says that it is being pulled, and I drew it going to the left. We did not specify a direction, so if a direction isn't specified, you choose a direction. This one I drew going left. So we have a pull force to the left. We haven't said what it is. Is it a rope? Is it somebody's hand? We don't know, but we know there is something or somebody pulling. And we included this one. It didn't say that there was friction, but this is where we start to bring some of our background knowledge. It didn't say it's a smooth surface. We know that the sled is sliding across the ground, so there could be friction. So unless we hear otherwise, we are going to assume that there is friction. So we've done this inventory, and people might want to say, how do we know there's not any other forces? Well, is there anything else touching the sled? We've already said this could be a hand or a string. We know the earth pulls down and the gravity doesn't need to be touching, but pretty much everything else does. The package is touching it and it's pushing down. The ground is touching the sled and it's pushing up. The ground is touching the sled, and this force of friction is the ground pushing backwards. So both of these, the friction and the normal force, these are forces from the ground. This is the force from the hand or rope. This is the force from the package. And then here's earth pulling down. These are all outside things. And I can't think of anything else that would be touching the sled, so nothing else that could really be pushing or pulling it. Okay, now let's write the equation. And I'm just going to repeat all the forces in one direction minus all the forces in the other. But there is one little trick to that. We do want to figure out if this thing is accelerating. So let's look at up and down. Is there any up or down acceleration? These forces pull down, this force pulls up, but the sled does not move up or down. And if the sled doesn't move up or down, that means its acceleration is zero. It can't change y velocity if there is no y velocity. What about x velocity? Well, we know it's moving. Is that velocity changing? Yes, it said it's speeding up. That means it's increasing in the direction that it's being pulled. So our x acceleration is to the left. And I would even encourage you on your free body diagrams to go ahead and say, if there's an acceleration, to show what direction it's in. This sled is accelerating to the left. Why is this useful? Because we know that whatever direction the acceleration is in, that has to be a larger force. So larger force in the direction of the acceleration, minus opposing force, minus anything opposite, equals max. What about for up and down? Well, if there is no acceleration, then it honestly does not matter. I could take all the forces up minus all the forces down, force of the package, force of gravity, equals may. Or we could just as easily write force down plus force down minus force up, and both of these equations would be true. Why are they both true? Because in both cases, since my y acceleration is 0, what we can figure out here is that the normal force is enough to cancel out both of these together. Well, what's happening here? Both of these together cancel out the normal force. They're telling us the same thing. So either of these equations would work for the for the y. Here's my equation for the x. Now, let's see what this might look like with some numbers. Let's ask ourselves, if the sled has a mass of 10 kilograms, if the package has a mass of 2 kilograms, if the force of friction is, I don't know, let's say 5 newtons, and the force of the pull is 15 newtons. Let us see if we can figure out what the normal force is, what the x acceleration is. Let's figure out everything that we can, and we have all of the tools that we need. So first, let's follow through on a couple little givens here. If the mass of the sled is 10 kilograms, we know that the force of gravity on the sled will be ms times g. 10 kilograms times g, 100 newtons. What about the force of the package pushing down on the sled? Well, we can take a quick step back and say, all right, if I have my package, let's say, I don't know, it's tied with a little bow here, and gravity pulls down. How much does gravity pull down? Well, if it has 2 kilograms, then it will weigh 20 newtons. So what does the force of the sled have to be up on it? 20 newtons. Well, that's if the sled pushes up on the package with 20 newtons, the package is pushing down with 20 newtons. So, okay, 20 newtons for the package, 100 newtons for the sled. What does that mean the normal force has to be? You've probably already figured this out, but let's actually use the equation. We said force up minus force down equals MAY. Notice how we can go through here and say, here's my unknown, known, known, known. Okay, we've narrowed it down to a single unknown, which means this equation can help me actually find something. And you should do that assessment as soon as you write these equations. Okay, well, that means if I solve this, I will get that the normal force equals force of the package, I added that to the other side, force of gravity on the sled, I add that to the other side. So 20 newtons plus 100 newtons, and we get that the force normal, the ground has to push up on the sled with 120 newtons. And I should make sure to include my upward direction. What about figuring out the sled's acceleration? Well, once again, I had, with my net force equation, force in one direction minus force in the other equals MA. I did have to tell you what the pull force was, so that was given. We figured out that was 15 newtons. This was 5. And if these are not given, then we'll have to figure them out using some other method. We'll have to include some other information, because this equation will only be good for one unknown, and I already have one unknown. That's my acceleration. Everything else will have to be solved. If it's not given, will have to be solved in a separate problem. But I do know my pull force, I do know my force of friction, I know my mass, so that means I could go ahead and solve this, that my x acceleration is pull force minus friction divided by mass, and I could go ahead and put in 15 newtons minus 5 newtons divided by my mass of the sled. The object that we're talking about, the equation this was for, was the sled itself. The sled had a mass of 10 kilograms. And what I get here is 10 newtons, which is kilogram meters per second squared. If I divide out those kilograms, I will be left with meters per second squared. And if I divide 10 by 10, I get 1. We get an acceleration of 1 meter per second squared. That's it.